So welcome back, friends. So we started with the Lorentz transformations essentially, okay, and then uh, now uh, we looked at x mu vector because x mu is essentially, we know that the line element in special theory of relativity, the main condition that the line element should always be near invariant under Lorentz transformations, and then we use this condition that the line element under Lorentz transformations should be how the line element transforms under Lorentz transformations is this condition essentially. Under this condition, okay, this is important. Now just using this condition, and the second condition that the line element should be invariant under Lorentz transformations, okay, using these two conditions we arrived at the following property that uh, that the transformation of the metric tensor would give me this particular property. The Lorentz transformations, because metric tensor transforms should be invariant and it transforms with two Lorentz transformations and it should be invariant. Okay, the metric tensor transforms with two Lorentz transformations and it should be invariant. Why does it transform with two Lorentz transformations? Because it has two indices. Now a vector with the 4 vector with one index transforms with one Lorentz transformations, and because the metric tensor is has two indices, it should transform with two Lorentz transformations. Under these two Lorentz transformations, the metric tensor should be invariant because the metric tensor doesn't change under Lorentz transformations. Because the metric tensor doesn't change under Lorentz transformations, we end up having the condition that we have the condition that there is a lambda for every Lorentz transformations. There is an invariant, the inverse of a Lorentz transformations, and this will be useful to keep the metric tensor invariant. So the first thing we have seen is that the Lorentz transformation, it has an inverse. Essentially, every Lorentz transformation has an inverse. Now if this is the case essentially, so what would be the inverse? Say for example a generic Lorentz transformation, okay, lambda, let me change the color, okay, the lambda lambda is equal to lambda 0 0, let me write it this particular fashion, 0 1 in the most general format, lambda 0 2. I am filling up all the elements essentially in terms of some notation essentially, lambda 0 1, lambda 1 0, lambda 1 1, lambda 1 2, lambda 1 3, lambda 2 0, lambda 2 1, lambda 2 2 2, lambda 2 3, and finally lambda 3 0, lambda 3 1, lambda 3 2, lambda 3 3. Now lambda 2 2, lambda 3 3, lambda 1 1, lambda 0 0 are your diagonal elements essentially. Now from this equation what we can see, obviously immediately you see that if I change lambda inverse, what would be if I just change the 0 3 elements and the sign of the components, okay, which has, for which only one of the indices is 0, then it gives me back my inverse. So if I want to get my lambda inverse, this is nothing but lambda 0 0 minus lambda 0 1 minus lambda 0 2 minus lambda 0 3 minus lambda 0 1 minus lambda 0 2 minus lambda 0 3 and the rest of the elements will be exactly the same essentially, except that up and down indices would change. This would be 1 1, this would be 2 1, this is 3 1, this is 1 2, this is 2 2, this is 3 2, this is 1 3, this is 2 3, this is 3 3. Okay, this is the main thing, because what we know is G alpha beta. Okay, if you G mu has this form essentially. G mu, I wrote it in the morning. G mu has this form. This is nothing but your eta mu. Okay, G mu is equal to eta mu is equal to this. This has this form. Okay, if you change the inverse of one of these things, it will automatically change everything essentially. Okay, it gives me the inverse essentially. It's extremely easy to find the inverse of a Lorentz transformation if you given in a general Lorentz transformation format. This is what it looks like essentially. Okay, now what we have seen, now what are the 4 axioms of a group? Closure. Now if you have 2 Lorentz transformations, it also forms if you have a group of Lorentz transformations, let me call that group SL2C. We will see another form for it essentially, or let me form, there is a name for this group, this is called SO31. Special orthogonal group with 3 dimensions, 3 space dimension and 1 time direction, because the space time direction and time direction have a relative sign difference essentially. Okay, so it is not SO4, not equivalent to SO4. Okay, because it conserves the metric with an opposite sign. Okay, it doesn't, it conserves x0 square minus x1 square minus x2 square minus x3 square, but not x0 square plus x1 square plus x2 square plus x3 square. So it doesn't conserve this length, it conserves the line element which has a minus sign within the time element and everything. So such a group is called SO31. I am telling you the name right away. I am also telling you that it forms a group. Okay, that, okay, let's see. Okay, so 2 Lorentz transformations. Also form a Lorentz transformations. So it satisfies the group essentially, actually. Okay, it satisfies the condition that the 2 Lorentz transformation form a group. Okay, so if you have lambda 1 and lambda 2 belonging to this group, let me call this G for the present, essentially G, then you will see that that these are 4 by 4 matrices and these satisfy the condition. Okay, what should the condition they should satisfy? The condition they should satisfy is this condition, this red line condition. This is the condition which we can write it as 1 Lorentz transformation transpose G, which is nothing but your metric tensor G lambda should be equivalent to G. Okay, let me, I am introducing too many G's, so let me call SO31. So what do they should they transform? This condition should always be valid. So G is your metric tensor. So matrix metric tensor. So it should leave the Lorentz transformation should leave you the metric tensors invariant. Now what we have shown is that this is nothing but the transpose. It's an orthogonal group essentially. The inverse is nothing but the transpose. So that's the reason why we wrote down in this particular fashion. It forms an orthogonal group. So that group is essentially SO31 forms an orthogonal group. So what we wrote is the inverse would be the orthogonal. Okay, the inverse is nothing but the transpose essentially. Inverse in orthogonal groups. What we have seen is O transpose should be 1. So okay, in this case, but what they should leave, they are orthogonal, but they should leave. This can be written in terms such as a fashion that lambda transpose G lambda should be equivalent to G. Okay, that's what they should leave the metric invariant. This is the same condition. So if you have lambda 1 lambda 2 as two Lorentz transformations, okay, then we have lambda 1 lambda 2 product transpose G lambda 1 lambda 2. Okay, this is equal to, this is very easy to show that this is nothing but lambda 2 transpose lambda 1 G lambda 1 lambda 2. Okay, now this is nothing but your G by the above condition. So that means lambda 2 transpose G lambda 2 is also equivalent to G. So this lambda 1 lambda 2 is equal to some lambda a Lorentz transformation. Okay. So what we have seen essentially, you can see it in another way essentially. Okay, this is one of the easiest way to look at it in terms of the group theory essentially. You can see it explicitly. Okay, what we can do it actually. Okay, so what we are seeing here is just by using this condition that it should leave the metric invariant. But what we are seeing is that the product of two Lorentz transformations also forms a Lorentz transformation. So it belongs to the same group. So it is closure. Now you can say that instead of doing that, you can actually calculate explicitly. So you can say, now let me just write down what we wrote: gamma eta gamma 0 0 0 0 0 0 1 0 0 0 0 1. You can take two gammas, multiply them, gamma 1 gamma 2. Okay, sorry, let me, one can see this explicitly, like but that is not needed essentially. But anyway, just to mention you that you can write it as say gamma 1 eta 1 eta 1 gamma 2, and then no, I have not written it correctly. Okay, explicitly means take two Lorentz transformations. So let me write it down in terms of 4×4 matrices: gamma 1 eta 1 0 0 eta 1 gamma 1 0 gamma 2 eta 2 0 0. You can multiply this and you can show that it has a form. Okay, you can explicitly do this exercise and it has a form exactly again of some gamma 3 eta 3 eta 3 gamma 3. You have to use the velocity multiplication rule. It has this particular form essentially. You can explicitly show this particular thing that it is closure, but it becomes very tedious, this exercise essentially. Now you can ask, oh, now why I have a boost in x direction, what happens to a boost in y direction? Okay, do they also meaning become a third Lorentz transformation? Yes, it is true, but we have taken simply both in x direction essentially. So you can do the same exercise, explicitly show that there are two in y x direction and one boost in y direction gives me another Lorentz transformation which has some combination of x and y essentially, and x and z and so on. So essentially you can play around with it, and of course if you do that, it is a tedious exercise to show, but if you do the way we have done so far, which is simply to just show that the condition that the metric is invariant, it's obvious that they all form Lorentz transformations. Okay, so that is the power of sort of group theory in some sense. Essentially that's the power of group theory. Okay, now similarly once you believe this, the associativity becomes automatic. Lorentz transformations associative. Okay, so lambda 1 lambda 2 becomes lambda 3 is equal to lambda 1 lambda 2 times lambda 3. Okay, you can do the same thing what we have done for closure. Essentially you can use the same exercise what we have done, just say that lambda 1, it doesn't matter whether I multiply lambda 1 lambda 2 first and then multiply with lambda 3. Oh, I should, there is an error in this equation. Okay, and the brackets are wrong essentially, or if you multiply lambda 2 lambda 3 first, and but the order should be the same essentially. The order, as long as the order is the same, lambda what I mean was you're not interchanging lambda 2 lambda 3, the order essentially, as long as the order is the same. The way you multiply lambda 1 lambda 2 first or then multiply with lambda 3, or you multiply lambda 2 3 first and then you multiply with lambda 1, it doesn't really matter essentially. So this for this you can do the same similar thing what we did. This will leave you the metric invariant, and the condition that the Lorentz transformation should leave the metric invariant also show that the associativity formula, associativity is always valid essentially. Lorentz transformation is valid. Okay, good. Now then the important point which comes is essentially existence of identity. So there is an identity matrix. So I is equal to lambda g mu nu, one up and one down essentially. Okay, or this is equivalent to delta mu nu. It's obvious because if you have if you have the condition that g mu nu is equal to lambda mu rho mu sigma is equal to g rho sigma. Okay, or we wrote it this particular thing as some lambda g lambda transpose is equal to g. When lambda is equal to I, this is always obvious essentially. This is obvious. So this is obvious. There is an identity element in the group of Lorentz transformations in the group of Lorentz transformation. So this proves. Now, I just want to make one more connection here. Essentially, I mentioned why the group is SO31. I mentioned that this is a special orthogonal group of 3,1 essentially. Okay. Now, if you remember very well, essentially that in the classes I mentioned that uh, in all these groups, orthogonal groups or continuous groups and everything, they all start with a identity and then with tiny transformations, minute transformations around that particular identity. Essentially, you can always tune around the identity essentially and make small rotations. Okay, so small infinitesimal rotations around the identity. So this tells you that this can be expressed in terms of some class of orthogonal matrices. Essentially, this tells you this can be expressed in terms of a continuous Lie groups essentially. Okay, it's a continuous Lie group. That means that you can express all the elements in terms of generators starting because you can start with identity, make an infinitesimal transformations right in terms of generators, and that is precisely what we are going to do essentially. Okay, so first of all what we are trying to show is that the Lorentz transformations form a group and then they form a special kind of group which fall into the category which we have been trying to understand so far, essentially the orthogonal groups essentially and rotational groups, and they are continuous Lie groups. Essentially they are continuous Lie groups. Okay, they are continuous Lie groups because they have an identity, so they can be expressed, as we will see that they can be expressed in terms of continuous tra transformations around the identity with infinitesimal transforms around the identity. Now what we have is that we already showed that existence of an inverse. So what we said that for every Lorentz transformation, we have shown it here. We have shown it that for every Lorentz transformation there exists an inverse. Of course, we can make the argument much more formal, but we can make it very formal, and we will. Okay, we will do it essentially. We don't have to show that essentially as of now, but for every uh, say for example for every lambda belongs to Lorentz group, there exists a lambda inverse also such that lambda inverse transpose G lambda inverse is equal to G. So that means it also forms a Lorentz transformation. It also forms a Lorentz transformations. Lambda inverse transpose G is equal to lambda into lambda inverse is equal to G. This is nothing but saying that lambda inverse transpose is nothing but lambda. Okay, this is nothing but saying that lambda inverse transpose is nothing but lambda. Okay, in a way, in some sense, showing that it's the inverse of lambda inverse essentially. So which is nothing but lambda essentially. So what we have, okay, we can do this formally, but that's not necessary. But we have seen it enough that for every Lorentz transformation, lambda, this condition is sufficient to show that this condition is sufficient to show that for every Lorentz transformation there is an inverse Lorentz transformation, which is good. Okay, we will leave it at it is, but now let's look at the four conditions we have seen. There is flow closure, there is associativity, there is identity, there is inverse. So this means the set of Lorentz transformations forms a group. This is the most important statement we have, essentially, that the set of Lorentz transformations forms a group. This group has a particular name, and uh, then the name is SO31. It's a special orthogonal group, but not in 4 dimensions, but 3 plus 1 dimensions, because we want to distinguish between the time direction with the space directions, because there is a relative sign difference between the space and time directions, essentially. So this group has time direction. Now the question now arises is, okay, Lorentz transformations form a group. Then still, what has it to do with the spinors? Okay, we'll come back. We are coming back slowly to the question that what had it to do with spinors. So that forms the question that what are the representations of the Lorentz group? Okay. So, what are the representations of the Lorentz group? But before doing that, we have to see what are the generators of the Lorentz group, what are they, and whether they form closed, compact or not. And then from there on, we can look at representations of the Lorentz group. So in the next lecture, I will do some properties, important properties about the Lorentz group before going into the building up of the representations of the Lorentz group. Okay. Thank you very much. We'll continue in the next class with the Lorentz group. Thank you.